Hello everyone, we are going to start basic theory of linear differential equations of nth order. We are going to start with considering initial value problem for homogeneous linear differential equations. So equation is going to have nth derivative plus p1, the coefficient function, and minus 1 derivative, and all the terms in between. The right side equals to g of t, which is non-homogeneous part, right? And we are going to consider also initial conditions. Initial conditions are set at point t0, and they're equal gamma 0, and derivative of t0 equals gamma 1, and nth minus 1 derivative at t0 equals gamma n minus 1. So in total, we have n initial conditions. What are gammas? Gammas are just numbers, right? Real numbers, whatever they are equal for the equation or physical problems they describe. They're just real numbers. Now, the theorem. You probably remember uniqueness and existence theorem we had somewhere in the beginning. So in this case, I'm going to just repeat this theorem. If we do have the coefficients p1, p2, pn, and the non-homogeneous function g of t, all continuous on interval a, b, and a and b can be both infinity or one of them can be infinity. Just interval is supposed to include point t0. Then the theorem tells that there exists a unique solution of this differential equation. Solution is going to be on the same interval or on some interval around point t0. Well, now we are going to introduce some new stuff to make our life a little bit easier. We're going to start with introduction of linear operator. Linear operator we're going to use to make our notes shorter. So we're going to call the whole left side of our equation with nth derivative up to the function itself, L of y. L of y is going to be a linear operator. Linear operator is a function which works on other functions, and it's supposed to have two major properties. Let's kind of review definition of linear operator from linear algebra. So an operator L is called a linear operator if for any two functions, well, from the set of functions on which it works, functions f and g, and any scalar constant c, next two statements are true. First, linear operator of the sum of these two functions is equal to a sum of two linear operators. It's one part of linearity, and the second linear operator applied to the constant multiplied by a function equals constant multiplied by a linear operator of the function. So we are going to check our linear differential operator L if it satisfies both conditions and it really makes linear operator. So condition number one, it converts sum of two functions into sum of the operators applied to functions. So we are proving that linear operator applied to functions y1 plus y2 equals linear operator of y1 plus linear operator of y2. Well, how are we going to do it? We're just going to plug in these two functions into the equation and then simplify our expression. We are going to use the fact that derivative of the sum of two functions is a sum of two derivatives. And you see that everything makes two linear operators. You just kind of separate terms with y1 from terms with y2, and you are going to get just exactly same equation for y1 plus same equation for y2, right? Now, for the constant, we're just going to apply linear operator to the constant multiplied by y, right? Remember that when we differentiate constant multiplied by a function, we can always take constant outside. And basically that's going to prove our statement, right? We can take constant outside from every point where the function sits, no matter whether it's function or a derivative, and get a very same equation we had before, just without constant. Which means that we can kind of take constant outside of the operator. The question is, why does it work? Well, first, it works because our equation is linear about y, so it does not have any other powers of y or any other functions of y, just the first power of y. And second, because differentiation is linear, so the sum of two functions, if you differentiate it, is going to give you sum of two derivatives, right? And if you well, if you check the equation, it's linear about y. It means that you don't have y squared or sine of y, for example. It's just like y with coefficient or derivative of y with coefficients. Only first powers of y are used. And the second one is that differentiation, as you remember from calculus, if you apply it to the constant multiplied by a function, you can take constant outside of the derivative. Let's see how it looks. I'm going to write it down. So derivative of a constant equals constant multiplied by derivative. So these two kind of facts about differentiation and linearity of our equation are providing us with linear operator L. Well, very good. Now we are going to write our equation much shorter. Instead of writing down like bunch of derivatives multiplied by coefficients equal g of t, we're just going to write down linear operator L of y equals g of t, which is nice, right? Well, we're going to move it to a theorem. If functions y1, y2, y3, yn are solutions of homogeneous linear equation. Let's write it down. L of y equals 0, so we don't have g of t. G of t equals to 0, homogeneous equation. If n functions are solutions n, linear combination of these n functions is going to be a solution too. Yeah, and I think it's better to use a different letter M instead of letter N here, just because, well, right now we don't know how many of these functions supposed to be, right? So we can combine any number of solutions together and they are going to make a solution. So I'm writing down the fact that linear combination is going to be a solution. Now, the proof. Well, proof is going to be very easy and it's going to follow from linearity of differential operator rate. We do know that functions y1, y2, and ym are solutions. Solutions means that if you plug them into the equation, you are going to get 0. And I'm writing down this fact on the top, like L of y1 equals 0, L of y2, so they are solutions. Now, is linear combination is going to be also a solution? So are we going to get 0 also? Well, we're going to use properties of linearity of our linear operator and just kind of open these square brackets. C1, Y1, right? So first we kind of split it into n terms, or m terms, let's say better. And after that, take constant from each term outside. And we are going to have a bunch of constants multiplied by linear operator applied to the function, right? You do see that because they are actually y1 and y2 and yn are solutions, so they are going to give me 0. And we are going to have a bunch of constants multiplied by 0, which is going to, of course, give us 0, so we prove it's 0. So if you have several solutions, you combine them with any arbitrary constants, and you are going to get a solution again. This happens because our equation is homogeneous and linear. Okay, now, the big question will be, can we represent any solution of this homogeneous equation with initial value problem as a linear combination of these functions, which are solutions to? I'm going to write it down. Why do we need this? Well, because if we find, for example, n different solutions of homogeneous equation, remember how the strategy was working. We find solutions, we add them together with their arbitrary constants, then we calculate constants using initial conditions, and that's going to be our general solution, right? The question is, maybe there is some other function, phi of t, which does not fit into the general solution. So, do we have this phi of t? Can we have some unexpected solution besides what we found, or no? And the second question appears like, if we do have n solutions, what are conditions on these n solutions? Any n solutions are going to work, or maybe we should put some conditions on them, and that's going to be not any n solutions, but certain n solutions of this differential equation. Well, we're going to try to answer these questions. If we can represent any solution through the linear combination of known solutions, like n known solutions, we don't need to look for any possible solutions because they are all going to sit in this linear combination. We can find just n solutions and then kind of write down this linear combination. And if somebody gives us initial conditions, we're going to just plug our solutions and calculate the constants. Now, let's imagine that we can do it. Let's imagine that we can actually represent any arbitrary solution of our homogeneous equation as a sum of n solutions multiplied by constant linear combination. Because y1, yn are solutions, phi of t is going to be solution 2. We just proved the theorem, right? A linear combination of solutions is a solution. And let's kind of apply our initial conditions to both, to function phi of t and to our, known functions. Let's see how it's going to look. So I'm going to write down like two columns. First is going to consist out of phi of t, and I'm going to plug in t0, and my first initial condition is gamma 0, right? And the second side, my right side, is going to be made out of linear combination where I plug in the very same t0 and kind of make it equal to gamma 0 or to gamma 1, depending on what is this. First derivative is going to be gamma 1, and until we reach the last derivative, which is n minus 1, right? So guys, let's look at this system. Let's look at the right side of the system. What are gammas? They're just real numbers, right? What are going to be y1 and yn of t0 and derivative of y1 and yn of t0? And all of them are going to be just numbers too, because after you have the function, you plug in t0, it's becoming a number. And even if you differentiate it, plug in your t0, it's still going to be a number. So we do have the column of numbers gamma. We also have all numbers in y's. The only unknowns are going to be the constants, right? We have a system of n equations with n unknowns. So constants C1, C2, C3, and Cn are unknowns, but everything else in this equation is going to be known. The question is, well, what are conditions under which we can find the actual solution? Because if we find the solution, we can use the solution and it's going to be very good for us. So we can represent phi of t through the linear combination, right? And because this phi of t and linear combination are going to fit same initial conditions and solve same equation, they must be identical because we just had a uniqueness theorem before, right? Remember, if we do have two solutions which satisfy same equation, same initial conditions, they must be a same solution. Uniqueness theorem, right? Same over here, right? If you have two functions, one phi and one linear combination, they satisfy same initial conditions and they solve same initial equation, they must be same. So any function phi can be represented as a linear combination. Well, now we are going to figure out like what are conditions or like what's supposed to be these functions, why. From linear algebra, we remember that when you want to solve non-homogeneous system of n equations, the only way for it to have a solution for the constant C1, C2, and Cn, a unique solution, is that determinant of the system is not equal to 0 if you want to have a unique solution. Well, that's what we want, right? Because if our solution is not unique, then it's not a real solution because we do have uniqueness theorem, which tells that solution is unique. So I'm writing down the determinant of the coefficients. In this system, coefficients are actually going to consist of the functions. You can look at this determinant, and it's like linear algebra tells us that if it's not equal to 0, then there is a unique solution for constant C1, C2, C3, and Cn. I'm going to write down this system in like more matrix form. So this is a matrix of coefficients. So y's are actually, they were functions, but now they are coefficients because we plugged in T0. C1, Cn is a count of constants which we are searching for, unknowns, and gammas are the right side, like b. So remember, ax equals b. So, well, we don't know if it's true, right? Determinant can be equal to 0 or can be not equal to 0. So let's find out like how it works or what it's going to be, or when determinant is not equal to 0, and that's going to help us to actually represent it or solve it. By the way, determinants of a system of n functions made like this, like the first row is the functions, and the second row is first derivative, and then second derivative, and then until you reach n minus 1 derivative, are called Wronskians. I'm going to write it down. Well, Wronskians are determined not only for solutions of differential equations, they determine for any set of n functions. So you write down like functions as a first row, and then derivatives, and then second derivatives until you reach derivative n minus 1. You're supposed to have n rows and n columns in your matrix. Okay. Let's kind of, because we want to answer the question like what are the functions y1 and yn to give us this determinant not equal to 0, we're going to talk about linear dependence or linear independence of a system of n functions. Like remember, in linear algebra, if determinant is not equal to 0 means that vectors are linearly independent. Here we are going to talk about functions. So a set of functions, any functions, f1, fm, like m functions, is linearly dependent on interval I, and interval I can be from negative infinity to positive infinity, or it can be just between two numbers. if for a linear combination of these functions, like you multiply first function by C1 and second by C2 and like m function by Cm, we have non-trivial solution, which kind of means that not all constants C1, C2, Cm are equal to 0. If we do have a solution which makes this statement true, then the system is called linearly dependent. So we have non-zero solution of this equation. Solution means for the constants. So we do have non-zero constant set. Well, I'm going to consider a couple of examples to show you like how it works. For example, consider f1 equals x, f2 equals x squared, and f3 equals x plus x squared. Well, obviously f3 is made up of x squared, which are functions f1 and f2. I'm just making up this simple example. And if you move everything to one side, for example, to the right side, you are going to have a linear combination of these three functions, and the constants in this linear combination are not equal to 0. Constant 1 equals 1, constant 2 equals 1, and constant 3 equals minus 1. And this linear combination is always equal to 0. If you plug in these constants, the sum is going to be equal to 0. Let's calculate what is going to be the Wronskian of this system. So I'm copying the functions x, x squared, x plus x squared, derivatives 1, 2x, and 1 plus 2x, and the second derivatives 0, 2, and 2. I'm going to calculate the Wronskian using decomposition by the first row. So x multiplied by the determinant of 2 by 2 matrix, which sits like which I circled, and then minus x squared multiplied by the determinant of the matrix of like leftover rows. In our case, it's 2. And the last one is x plus x squared multiplied by 2, because leftover matrix here also is going to have determinant of 2. We do have 1, 0 here, which kills almost all terms. If you open parentheses, you see that lots of terms are going to cancel, and eventually we are going to end up with minus 2x plus 2x, and determinant of Wronskian is going to be equal to 0. So we can start making a connection. The system is linearly dependent and determinant is equal to 0. Now let's consider a different system. Well, first function is 1, second function is x, and third function is x squared. And the same question, is the system dependent or not dependent? Independent. Okay, let's build up linear combination and see if we can possibly find solutions for C1, C2, and C3, which makes this linear combination identically equal to 0. You know that this linear combination, if you look at it like from the point of view of x, it's just a quadratic equation. We do know that quadratic equation is going to have either one real solution or two real solutions if the constants are not equal to 0. So if we do have some constants like C1 or C2 or C3 are not equal to 0, we are just going to have several solutions, one or two. But it's never going to be identically equal to 0. So we know that parabola is not like something which is equal to 0. Parabola is always going to have just maybe one or two intersections with x-axis, but not all parabola is along x-axis. So there is no way to pick up constants which are going to solve this and be non-zero. Let's calculate the Wronskian. We see that because constants are zeros, to make it working, we are going to have independent system. Wronskian of this system, I'm rushing a little bit through it, is going to be equal to 2. Well, I just copied the functions, first derivatives and second derivatives. So you see that the functions are linearly dependent or like linearly independent. It's connected to the Wronskian. You see that the Wronskian is not equal to 0 and they are independent. You cannot find a constant. Wronskian is equal to 0 and they are dependent. We're going to have a general theorem about this. But the theorem is not going to be about all functions. The theorem actually is going to be just about solutions of this linear operator. We're not going to like prove general theorem about Wronskian and linear dependence. So, linear dependence and the Wronskian. 4 solutions of our differential equation. So we're not going to consider Wronskian for all possible functions, like we just did systems, right? we're going to consider only solutions. Well, for solutions, Wronskian is going to look very nice actually. So the theorem, if you do have n solutions of the linear differential equation of nth order homogeneous, and the coefficients of this homogeneous equation are continuous on interval, then we can have only two possibilities. Either these n solutions are dependent, and then Wronskian at t0 equals to 0, and the Wronskian at t equals to 0 too. T0, Wronskian at t0, it's 1 point on Wronskian. Wronskian is actually a function, right, which is going to depend on like variable t or x. So a function is going to be either equal to 0 at 1 point and equal to 0 everywhere, or if they're independent, it's going to be not equal to 0 at 1 point, like t0, and not equal to 0 nowhere. Interesting, right? It's either 0 or non-zero. In the second case, we are going to call the system a fundamental solution set. So if you do have n linearly independent functions and the Wronskian is not equal to 0, then we are going to call these functions a fundamental solution set. Well, let's prove the theorem. To prove this theorem, we are going to start with proving first Abel's identity. Abel's identity is going to actually show us how Wronskian is going to look for this nth order differential equation. So Abel's identity, the Wronskian of n functions y1, y2, yn equals Wronskian of same n functions at point t0 multiplied by e to the power of minus integral of t0 t p1 of x dx, and I'm going to prove this for the for the second order equation. So let's consider y1 and y2, which are solutions of the second order equation. Well, second order, two solutions, right? And let's just write down that solution y2 solves the equation and solution y1 solves the equation. And I put y2 above y1 on purpose because I'm planning to subtract these equations from each other. I want to subtract the lower from the top. So let's multiply first equation by y1 and second equation by y2 and subtract them. Try down the difference. I'm first subtracting the terms with second derivative, then terms with first derivative, and last terms with just like the function itself. You see that the last term has exactly like same y1, y2 subtracted from each other. So last term disappears. The term with first derivatives does look like a Wronskian actually. If you look at the Wronskian of these two functions, it's y1 by y2 second derivative and y1 first derivative by y2. So we do see that the last term is Wronskian. What is the first term? The term with second derivatives. Well, because I do know this, I'm going to just kind of pretend that I guess, but actually I do know that if I take a derivative of the Wronskian, which is like y1, y2, and y1 first derivative, y2 first derivative, just basically of this difference. Well, using product rule, I'm going to take a derivative from y1, multiply by derivative y2, and then take a derivative of y2 and multiply by y1. Derivative of y2 is going to become the second derivative, and then repeat the same with my second part. You see that I have two identical terms, which I'm going to cancel, and I have two leftover terms, which are exactly the same as my first term in the difference of two differential equations. So actually what we have on the first position is a derivative of Wronskian. And we got a differential equation for Wronskian. So Wronskian derivative plus P1, sorry, I'm missing the label P1. Multiplied by Wronskian equals to 0. Well, we solve it as a normal regular differential equation, right? We separate variables here. And d Wronskian over Wronskian equals minus P1 dt. Let's imagine that our variable is t. Well, we know that the left side is going to give us ln, and the right side, because we don't know P1, what is the coefficient function in front of the first derivative, we're just going to keep it as an integral. And if we kind of take e of both parts, we are going to have a constant multiplied by the integral of P1 dt. And again, P1 is not a number, it's a function of t. For constant coefficient equation, it's going to be a number, but generally it's a function. Now, what is the constant? Imagine that in our integral, we set it like a definite integral from t0 to t. And what is going to be the constant? Well, we plug in t0 into Wronskian, and we are going to have Wronskian at t0, right? Because integral is going to be e to the power of 0 equals to 1. And our constant is going to be just Wronskian at 0. So, what we see actually is that generally Wronskian is Wronskian at point t0 multiplied by exponential function. We remember that exponential function is always greater than 0. It's never equal to 0, and the only way that Wronskian can be equal to 0 is that the coefficient, this Wronskian at t0 is equal to 0. So they are kind of connected to each other. If the constant or this Wronskian at t0 equals to 0, the general Wronskian is equal to 0. If it's not equal to 0 because it's multiplied by a non-zero function, it's going to give the general Wronskian not equal to 0. You see? Okay. So we proved the theorem actually, right? We did the identity and then proved the theorem. Now, new theorem. If we have n solutions of homogeneous linear equation L of y equals 0, there are two options for them. Either they are linearly independent and the Wronskian at t0 is not equal to 0, or they are linearly dependent and the Wronskian at t0 is equal to 0. Why do we like Wronskian of t0? Well, because that's our initial conditions, right? We plug in t0 and we can kind of calculate all values of initial conditions. I'm going to start proving with B part of the theorem, and I'm going to do the proof like if the functions are dependent, then Wronskian is equal to 0. So if they're dependent, then means that linear combination of the functions has non-zero solution. There are some constants which are not equal to 0, and this equation is making a true statement. Well, what does it mean? Let's differentiate this equation. Well, constants are going to stay as constants, but functions are going to give the first derivative. And let's differentiate it n minus 1 times. So we get all the lines in our system, right? So we get line number 1, line number 2. Now, number n is going to be actually the system of n equations and variables. We already do know that it has a solution because constant c1, cn are solutions. So the determinant of this matrix must be equal to 0. If we plug in t0 into our functions y, then y's are going to become numbers, and they are just going to make up a determinant of the matrix, which is going to be equal to 0. And then, on the other hand, is going to be equal to the Wronskian. I'm writing down the matrix which consists out of y as a big Y, and the constant c1, c2, c3, cn as a vector c, and 0 vector is like right side. So remember, if homogeneous system has a solution, means the determinant must be equal to 0. So in our case, matrix y, determinant of which must be equal to 0. It's the same as Wronskian. So we kind of proved that if they are linearly dependent, then Wronskian is equal to 0. Okay, opposite direction. If Wronskian is equal to 0, then they are dependent. So here I was proving that from dependent follows that Wronskian is 0. Now I'm going to prove opposite. That from Wronskian equals to 0, will follow that they are dependent. Well, basically, I'm going to write down the same system, right? And tell, okay, if the Wronskian of this system equals to 0, then the system has non-trivial solution. We know this from linear algebra, right? When determinant is equal to 0, the system has non-trivial solution for the constants. So that means that linear combination is going to be identically equal to 0 if we put this linear solution into this linear combination. So it means that functions are linearly dependent. Now, I'm going to prove A from contradiction if I'm going to kind of consider, for example, let's imagine that my functions are linearly independent, but Wronskian is equal to 0. Well, I already proved that if Wronskian is equal to 0, then they're independent, so I got a contradiction. And I'm going to repeat it opposite direction. Well, so basically I did the proof in B of B, and A is just kind of referring to B back. So now I'm going to try to do it opposite direction. So I'm going to consider that Wronskian is not equal to 0, but assume that the functions are dependent. Let's Wronskian be not equal to 0, but assume the functions are dependent. Well, if they are linearly dependent, B, the part of proof B tells us that they're supposed to give us Wronskian equals to 0, which contradicts to our kind of initial conditions that it's not equal to 0. So basically we proved the theorem. Well, now we are ready to set up conditions on functions y1 and yn, the set of the functions, which can help us to represent any solution phi of t. So you see that conditions are supposed to be, the functions supposed to be linearly independent, because if they are linearly independent, then they are going to give us a unique solution for the constants with like initial conditions. And we can represent any functions by fitting these constants into initial conditions. And well, guys, we already seen it, right? So the set of y1 and yn supposed to be linearly independent. Then we can find the constants which are going to satisfy same initial conditions on function phi, and by uniqueness theorem, both linear combination and phi are going to be solutions of the same equation with same initial conditions, which means that they must be identical. I'm going to write it down for the people who are not watching my lectures, but kind of reading my notes. And uniqueness theorem, I introduced it in the beginning of the lecture. I did not name it as uniqueness theorem, I don't know. I'm supposed to write it down explicitly probably. Well, we've seen it already. That is why we were looking for a solution. Remember, we were looking for a solution y equals t e to the power of rt when we had repeated roots, right? Remember, for repeated roots, we have just one exponential function, and we search for the second one multiplying by t. Basically, guys, we are looking for linearly independent solution. And exponential function multiplied by t are going to be linearly independent. Let's just kind of check it using Wronskian. And it's a little bit simpler explanation than the one I was giving to you when I was considering the repeated roots, and you remember probably reduction of order. Well, I'm going to use Wronskian to check if these two functions are linearly independent. We already know that they give us a solution and kind of we proved it like at least two different ways, but let's apply the theory we just developed in this section, general theory. And this general theory works not only for constant coefficients equations, which we used to solve, right? It works also for any linear equations of nth order. You see that the result of our Wronskian is equal to e to the power of 2t, which is always greater than 0 and never equal to 0. So Wronskian is always going to be positive for these functions. Not equal to 0 means that these two functions are linearly independent. I'm going to consider a couple of practice problems. Problem 1, consider three functions, f1 equals 2t minus 3, f2 equals 2t squared plus 1, and f3 equals 3t squared plus t. And I'm asking the question, are they dependent or not? Well, I'm going to start solving Wronskian, right? So for the first line, I just copy the functions. For the second line, I differentiate it. Very easy to make a derivative, right? And for the last one, I take a second derivative. Well, now I'm just going to expand by the first column, I think, because I do have a 0 in it. So it's 2t minus 3 multiplied by determinant of like 4t, 6t plus 1, and 4 and 6. And minus, so that's the determinant which is in first parenthesis, minus 2, and the determinant of leftover, which is 2t squared plus 1, 6, and 3t squared plus t, 4. If I multiply everything and simplify everything, which is like, 6 by 2 is 12, and 4 by 3 is also 12, but 1 is with plus, 1 is with minus, cancel. And I'm going to have actually several terms left. I'm going to open parentheses and have minus 8t plus 12 and minus 12 plus 8t. And that's equal to 0, so the functions are dependent. For next problem, I'm giving you a set of three functions. One is 1, the first one is 1, the second one is x, and the third one is x cubed. And asking the same question, are they dependent or not?